Yeah, the second paper in this track is titled An Approach to Overcome Modeling Inaccuracies for Performance and Simulation Sign-Off of High-Speed SerDes. The authors are Aneesh, Ranjan, Gaurav, and Pankaj Singh, and they are from Cadence Design Systems. So um, over to the paper presentation.
Hello everyone, welcome to our presentation. My name is Aneesh and I would like to talk to you on the topic an approach to overcome modeling inaccuracies for performance simulation sign-off of high-speed SerDes. Our team members are Aneesh, Gaurav and Pankaj. We all are from Cadence. The slides are divided into three parts: introduction part, implementation details part, and results and conclusion part. Introduction is again divided into modeling requirements, available modeling methodologies, gaps or limitations with current modeling techniques, and how to overcome these gaps using improved RNM methodology. Let us start with a small description of the models. The figure shown here is that of an AMS design which has digital parts and analog parts. In order to simulate such a design, we need to run AMS simulations, which is highly accurate but have very long runtime. To speed up the simulations, we replace the analog or SPICE components with some kind of digital models. There are two types of models: pure digital or logic models and RNM or real number models. Pure digital models is the fastest approach, but it is not capable of transferring real data across analog boundaries, whereas RNM is capable of doing so. Figure shows here a comparison between different modeling techniques. As you can see here, RNM is good in accuracy as well as simulation speed. Because of this reason, RNM is the most preferred modeling technique nowadays. In RNM, we use a signal flow approach. We model either voltage or current using real number value. Now we know that RNM is the most effective way to abstract AMS functionality. But is it good to model all modeling requirements? The answer to this question is what exactly our modeling requirements are. Basically, an RNM simulation can be thought of either a functional simulation or a performance simulation. In functional simulation, the focus is on verifying digital algorithms and the integration between analog and digital. Whereas performance simulations, the focus is on verifying analog specifications and its impact on system. Performance simulation verifies system performance for various attenuation channels, corners, noises, etc. Here we look for the J-toll curves, settled adapted codes, eye diagrams, etc. Because of this reason, performance simulations need highly accurate models. RNM is a good choice for functional simulation models, but when it comes to performance simulation models, there is a clear modeling gap. In our next slide, we'll see what those modeling gaps are. Figure shows the block diagram of a simple SerDes. There is a transmitter which transmits ones or zeros, and this transmitter pulse goes through a channel which provides frequency dependent attenuation to the input, and this output finally goes to an RX. In the RX, the equalizer equalizes the signal. That is, it provides frequency selective amplification to the input signal, thereby retrieving the original signal back from the attenuated signal. Now, in order to verify the system, we need the models to model the frequency dependent behavior of channel and equalizer. That is the attenuation of channel and gain of equalizer, and all its equalizer settings have to be modeled properly. Besides, the signal impairments associated with the system like noises, non-linearities, jitters, etc. also have to be modeled. In RNM, there is no clear industry methodology to model these items. Through this paper, we propose techniques to model the frequency dependent behavior and signal impairments. More details on this will be discussed in the coming section. We know that modeling frequency dependent behavior is an important part in modeling the response of a system. Let's see how this was done before the proposed methodology. Before proposed methodology, we were using a setup called capture and playback setup to capture the frequency dependent behavior. We have two parts here, a capture part and a playback part. In the capture part, we have a standalone schematic test bench. And using this test bench, we capture the output of the block to be modeled. We use a single cycle of predefined input data pattern and capture the output. Now, in the playback setup, which is an RNM setup, we replace the RNM model of the blocks whose frequency dependent behavior is to be modeled, and then insert the output from captured phase to the output of the model. Now, this setup has a lot of advantages, and it can clearly model the frequency dependent behavior of the block, but it has a lot of limitations also. Main limitation is that for each test pattern, channel, or corner, we need to repeat the procedure of capture and playback, which is time consuming. We also do not have the ability to provide random stimulus as input to the block. There is also difficulties in sampling, retiming, and interpolating the capture data. All these limitations force us to go back to pure RNM models for performance runs. This is a comparison between existing methodology and proposed methodology. In our proposed methodology, we have a single RNM setup for functional checks and performance checks. Because of this, our models now need to be highly accurate and close to schematics as possible. It needs to model the frequency dependent circuit behavior and the signal impairments to make the models highly accurate. This is how we implement the proposed methodology. We have 3 ways to implement the frequency dependent schematic behavior. It depending on the schematic size and the availability of transfer function, we choose one of these 3 techniques. 4 of the signal impairments are modeled here. They are noise, nonlinearities, gain compression, and jitter. Finally, by using these techniques, we were able to create a holistic approach to overcome the limitations of RNM for both functional as well as performance simulations. We are done with the introduction part. Let's see how we implement this. So the implementation details is split into 2 parts. One is modeling frequency dependent circuit behavior part, and the other is modeling signal impairments part. The frequency dependent circuit behavior is modeled either as a digital filter or as a structural model. And the digital filter again can be modeled using MATLAB or using bilinear transformation. This slide talks on how to implement a digital filter model. The filter model can be either IAR or FIR. We take the block to be modeled and then split it into 2. One part is the frequency dependent behavior part, and the other part is other functionality or logic part. We create separate models for other logic part and frequency dependent part. Finally, we instantiate both these models inside a wrapper model, which will be the outer model. Now, the key challenge of this method is to obtain the filter coefficients for the digital filter model. Based on how we obtain the filter coefficients, we have 2 techniques. This slide talks on obtaining the filter coefficients using MATLAB. This method is used when our circuit size is big and that the transfer function is not known. We use the MATLAB STMCB function to create the IR filter coefficients. This function takes 2 things as input. One is a step response of the input, a step response of the circuit, and the required number of poles and zeros. The procedure to create the step response is shown here. We run an AC analysis of the block to be modeled, and from the AC response we create the impulse response, and from it we create the step response, and finally save it in CSV format file. All these conversions are done using skill scripts, Virtuoso skill scripts. And finally, the CSV input file is used as input by the MATLAB code, which generates the filter coefficients. And now these filter coefficients are updated in the filter model. The filter model is implemented using system Verilog, and a direct form 1 structure is implemented here. These are sample waveforms. This is that of a channel. This is that of an equalizer, and this is the frequency response waveform. The channel waveforms, we have a cascaded programmable RLC channel, and as the number of cascaded RLC stages increases, the attenuation is increasing. As you can see here, with 15 stages of RLC, we have heavy attenuation, and we are not able to recognize ones or zeros from the output. In the second waveform, the equalizer is properly equalizing the input, and we are able to recognize ones or zeros properly, whereas in the channel output we were not able to. The frequency response comparison between models and schematics is shown here. There are around 64 settings of equalizers, and each of these settings frequency response is plotted, and the frequency response between models and schematics is matching. The second method of filter coefficient generation is using bilinear transformation. This is used when we want to create generic channel or equalizer models, especially aimed at testing digital algorithms or fast bring up. Here we have a S-domain transfer function, and using bilinear transformation, we create the Z-domain transfer function, from which we take the filter coefficients and update our filter models accordingly. These are sample waveforms of an RLC circuit. The waveforms are similar to the waves which we saw before. This slide talks on creating the frequency dependent circuit behavior model using electrical equivalent data types. Here we use system Verilog concepts of UDT and UDR, that is user defined type and user defined resolution. This type of modeling is used to create structural models that accurately resemble the schematics, especially schematics with minimal components like RC can be modeled using this technique. Here, using the UDT and UDR concept, we create an electrical equivalent data type, and using this data type, we create models for the basic components like R, LC, etc., and which can be used to finally create a structural model resembling the schematics. We do not have a signal flow approach here. Instead, we use electrical equivalent data type to model the voltage, current, and distance value associated with a node. The UDR can be used to create required rules like Thevenin's rule or Norton's rule, etc. This describes the language constructs used, and these are sample waveforms. A comparison of waveform from Z transform method and SV method is shown here. With this, we are done with the frequency dependent circuit behavior modeling. Let's see how we model the signal impairments. Signal impairments are modeled either as noise, gain compression, nonlinearities, or jitter. Noise is an unwanted random disturbances in an electrical signal. Noise of amplifiers and equalizers are captured here, and we use disnormal Gaussian disnormal system Verilog task to capture the noise. Sample noise waveforms and histogram of noise is shown here. It follows a Gaussian probability distribution as expected. The second signal impairment, gain compression, is a reduction in gain of an equalizer or amplifier for large signal input. When we are modeling the equalizers using digital filters created using AC analysis, we should model the gain compression following the digital filter. This is because AC analysis is not able to capture the gain compression associated with the schematics. We are using DPI-C function tan to capture the gain compression. Sample tan waveform is shown here. As the input increases, the gain decreases. The third signal impairment is non-linearity, which is the deviation of the output waveform from the ideal straight line curve. Non-linearities of phase interpolators are captured here, and we capture the INL or integral non-linearity. We run standalone simulations, schematic simulations to capture the INL values and later add it to a text file, which is instantiated in the wrapper model. This is how we model the INL. This is a sample INL waveform from a model. The jitter is a temporal deviation of a clock edge with respect to its ideal position. Jitter is present in input data stream and in PLL clock. We use 1 minus cos x function to model the deterministic jitter, and this normal system verilog task to model the random jitter. This eye diagram shows the presence of jitter, and this one does not have a jitter. These are sample waveforms. We are now done with the implementation details part. Before proceeding further, let's see how we capture the jitter tolerance information. We use a completely automated flow to capture the J-toll curve. This is more like a push button flow, and this reduces manual errors and saves time. This setup takes a suitable test case as input, and the setup creates multiple versions of this test case by varying jitter amplitude and frequency. Now a regression is run, and then a post-run script is run to probe the regression results. And then finally, the J-toll curve is plotted by capturing the boundary between pass and fail. With this, we are done with the implementation details part. Let's analyze the system results now. Figure shows the diagram of adaptation and equalization procedure. In adaptation, the equalization settings are changed to settle to the suitable equalization code such that we get proper equalization at the output. As you can see here, equalization settings are changing, and finally it settled to a equalizer setting. And now with this equalizer setting, we are getting good equalization because we are able to recognize ones or zeros properly from the waveforms, whereas from the channel output we were not able to. These are the eye diagrams. As you can see, the eye diagram is closed before equalization and it is open after equalization. This is for PCA Gen 4, this is for PCA Gen 3, and this is for 10 GKR mode. Now let's look at the J-toll curves. Using the proposed methodology, that is by modeling frequency dependent circuit behavior and signal impairments, we are now able to get a matching curve, that is the silicon and simulation data J-toll curves are matching. As you can see here, green one is the simulation curve and blue one is the silicon curve. Even without modeling signal impairments, we may get a good eye and passing J-toll curve, but sometimes the silicon data and simulation data may not match. With modeling the signal impairments and frequency dependent behavior, we get a matching curve and we can be more confident on our results. We are now towards the end of the presentation. Let's analyze the achievements using the proposed methodology. We were able to find a bug in the design using this methodology. In our simulations, the settled gain code was far off from the expected one, and upon further debugging, we found that the equalizer setting was not giving as much as gain as expected, and this turned out to be a schematic bug. As seen in our previous slide, using this methodology, we now get a realistic J-toll curve, and we are more confident in our results. Also, the system adapted code is now close to or equal to the codes as expected by the analog engineers, which gives us very good confidence. Overall, by modeling the frequency dependent circuit behavior and non-linearities, we were able to get accurate models, or we were able to increase the accuracy of the RNN models, thereby giving us more confidence in our simulations. In other words, we can say that by using the proposed methodology, we were able to push the blue RNN methodology to the green improved RNN methodology. We were able to get more accuracy with our models without much loss in the simulation speed. Finally, I would like to reiterate that using the proposed improved RNN methodology, we were able to provide a holistic approach to overcome the limitations of traditional RNN modeling approaches, and we were able to get good accurate results, which gives us more confidence on our data, simulation data. This is the last slide of our presentation. Here we discuss the next steps that we plan to do. One is to update our models with other corner informations, because as of now it holds typical corner information. And the second step is to update or explore alternate digital filter structures and modeling languages to improve simulation speed. With this, I am done with the presentation. Thank you.
That was really good. It take us to the details of the RNN model and how we got this to improve the frequency and the accuracy of the thing. One question I had, what is the kind of effort it takes to come up with this model? And how do you know the model is, I mean, how do you prove the accuracy of the model? Is it with comparison to what?
So the accuracy is proved with comparison to schematics. So what we do is like we have test benches to vary the frequency and then plot the frequency response of the models, and then we compare with the frequency response of the schematics. So we can overlap them and then see that it's matching.
Okay. And the type of effort it takes to come up with such a model?
So effort is, it depends on what type of model. So if you're going for some kind of generic models, the effort is less. But if you're going for the accurate models, like using MATLAB, then it could be like one week time or something. Like if first time it might take some time because we need to understand the procedures, etc. But later on it could be less than one week time.
Okay. Yeah. One last question from the audience. There was question is, did you explore a mix of the SPICE and the real number RNN model for balance of accuracy and performance?
So actually we haven't tried SPICE with RNN because our simulations the system frequency is above 5 gigahertz. So using SPICE, it takes long time to run the simulation. So that's why we went for RNN. And later on the requirements increased. Like initial requirements was just to check the functionality, but later on we had to see like how the I curves and JDL curves looks like. So we had to go for much improvements in the model, and that's why we came up with this modeling techniques.
Thank you very much, Aneesh. That was indeed an excellent presentation. And we'll just take a short break. I think we're running about 10 minutes late, I think, behind schedule. So we'll take a short break for about 3 minutes and we'll start the next paper in about 3 minutes or so.
Thank you.
Thank you so much, Aneesh. Thank you so much, Gaurav.
Yeah, thanks everyone.